Let f map the open interval 0 to 1 to the reals, be the function defined as f of x equals root n if x is in the interval 1 over n plus 1 to n, where it's closed and open on the left and right. Let g map 0 to 1 to r be a function such that the integral from x squared to x of square root of 1 minus t over t dt is less than g of x is less than 2 root x for all x in 0 to 1. Then the limit of x approaching 0 of f of x g of x does not exist, is equal to 1, is equal to 2, is equal to 3. Okay, there's a lot of stuff going on here. Let me write down the information we're given to start. Okay, how might I go about figuring this one out? There's a lot of stuff going on here, of course. So let's consider these two limits individually first, of f and g individually. As x approaches 0, g of x, well, this is always positive. So g of x goes to 0, right? And f of x will approach I guess it approaches infinity, right? Because as x gets smaller and smaller, the interval we fall into has denominators that get larger and larger, so this goes to infinity. F of x is essentially something like 1 over root x. I mean, of course, we might need to be more precise when computing this limit here, but it's something like 1 over root x. This might help us determine whether the limit exists or not. So I suppose then, f of x times g of x so if x is equal to, if x is slightly, okay, let me draw like an interval here. There's 0. Let's call this here a value of x. So then f of x is going to be equal to root n. Let's call it x naught to be clear that we're talking about a specific value of x. So f of x naught is equal to root n. And of course we have x naught is less than 1 over n. So n is less than 1 over x naught. Root n is less than 1 over the root of x naught. Okay, so f of x naught is less than 1 over the root of x naught. And we also have g of x naught, according to what we're given here, I mean, I suppose we have to, I don't want to think about what this integral is equal to too much yet, but given the way the problem is stated, we have to assume that this quantity is always less than that quantity. Is this integral easy to evaluate? I'll think about it later. Anyway, I'm just putting up an upper bound on this. This is less than 2 root x naught. And so f x naught g x naught is less than 2. This is for arbitrary x naught. F is always positive, g is always positive. Don't think we're going to get some kind of crazy oscillation thing going on. Is that possible? I don't think so. So I'm going to rule out option A. This function f times g is bounded according to what I've just done. It's less than 2, right? And it's positive. So unless it's oscillating in some wild way, and I don't see how that's possible unless it's, yeah. So the limit does converge to something. But what is it going to be equal to? Well, it can't be 3, right? So option D is also thrown out. Can't be 3 because the function is always less than 2. So maybe we need to put some kind of bound on this integral thing now and show that this function is always, this function f times g is always larger than something. Another thing I'm thinking about here, I'm kind of tempted to take a derivative wouldn't, this inequality for g will not be preserved by a derivative. So it's probably going to be a whole sequence of inequalities that we'll need to apply here. But, you know, if you go down the wrong path when you start messing with inequalities, you might never get to the wrong answer, and you might have to sort of just start again or backtrack. You know what we could do is maybe do something like here. Just let x and x plus 1, or x and x squared, let them equal to root n. In fact, that's what I might do. Let me finish writing this down and then I'm not really concerned with the, I don't think I need to touch the upper bound. Again, the 2 root x, I've used that as much as I think is possible. So this is going to be the same as the limit as n approaches infinity of f of 1 over, I guess I can do n f of 1 over root n times g of 1 over root n. And let's see what this turns into. Oh, you know what we could do is as x gets really small, this gets really small, and this numerator is basically 1, right? This is essentially 1 over root t in the integrand. So maybe I don't need to do this. I'll come back to that if what I'm about to do here doesn't work. For really small values of x, this is basically the same as the integral from x squared to x of 1 over root t dt. I mean, I've made this thing a little bit bigger for sufficiently small x, right? Like I've made this thing a little bit bigger. So this is a bit bigger, so this inequality might be violated for some values of x, but for extremely small x, you know, I'm kind of tempted to say that it's true. So maybe we can just integrate the left-hand side now. What does this function look like? So root x looks something like that. X looks something like that. So for really small values of x, you know, we get something positive. Okay, great. So the limit as x approaches 0 of f times g you know, f is something like 1 over root x, right? So this is something like 1 over root x. I guess I should say this is bigger than or equal to, bigger than with a question mark approximation of some sort. 1 over root x times 2 root x minus 2x, which is limit of x to 0, 2 minus 2 root x, which is 2. And I'm pretty confident in that then. You know, I might want to, if I wanted to do this, we're told that this inequality is true for all values of x. And so for sufficiently small values of x, if this is a strict inequality, you know, I think you might be able to argue that you can drop that and maintain that it might become a less than or equal to inequality. But you might have to do a lot of work to figure that out. But I think this is the answer too. I'm going to leave it at that. If I find a mistake in this or I have more to say, I'll put it down in the description. Thanks for watching.